Reminder, last reminder about the experiments. Well, for this week. I guess next week you guys are doing the calorimetry experiment, even numbered sections now. So odd numbers are done. And then even numbered sections, you're doing calorimetry. Make sure you're ready. Make sure you have all your stuff done the night before your lab. And it's your last real experiment, although you will be meeting one more time after Thanksgiving. All right, so now we are past Wednesday, so on to the next week. So homework due this coming Wednesday is Chapter 9, Part 3, which we are pretty much all done with. Chapter 10, Parts 1 and 2. So we're gonna get through probably most, if not all, of Chapter 10, Part 1 today, is the plan, and then Chapter 10, Part 2 on Monday. Okay, so quiz coming up on Tuesday will be Chapter 9 and Chapter 10. It'll be most of Chapter 10, including some stuff that we do on Monday. I know that's, right before the quiz, but I like to think of it as being fresh in your memory. But you guys can watch, some of those videos. I have all the videos posted from last semester. There's only 3 for Chapter 10, and only one of them is a full-length video. The others are partial videos because it's a really short chapter, Chapter 10. And then, reminder, please read all the announcements on Canvas. They're there to help you. All right, so I've introduced you to Cora before. This is Cora on the left, and then hiding behind her is Meanie, and then next to her is Miney. Not pictured is Mo. So we got 3 of these Brangus cows, and we called them Meanie, Miney, and Mo. Mo is not in this picture. All right, so I'm gonna start off a little differently today. So these polls are not, for any credit, but I will give you a disclaimer. I'm doing a class through Auburn University on the use of AI in classes. So one of my assignments is to poll you guys about your use of AI in classes. So there's no right or wrong answer. It's just for curiosity. Mm-hmm. You're using it right now. Wonderful. Yeah, that counts. All right. So just like 30 seconds on this poll, since it's not actually going to count for any credit. Get your answers in real quick. This is my my research of the day. Have you guys used any AI tools in any class, whether you were assigned to or not? I'm not asking any questions. Oh, yeah? Oh, okay. So this will probably all be yes. All right. All right. It's a bias sample. Okay. Thank you. All right. Thank you for your answers. If you didn't get your answer in, don't worry about it. It's not all yes, All right. I imagine this one will be yes. Have you heard of AI tools being used by your peers? So if you're not using it, are your friends using it? Or enemies? I don't know. All right, thank you. Get your answers in if you want to participate in my poll. Going once, twice. All right. All right, so this is a slightly different question, but if you've already used it for a class, then the answer is probably yes. But have any of your teachers discussed the use of AI tools in your classes other than right now? And I will probably post a discussion post on Canvas about it so we can talk more about it if you're interested. I know a lot of you are probably interested in it. So I'd like to hear what your favorite parts are or what your scariest parts are. All right. Anyone else want to participate in this poll? Going once, twice. So they're not going to count for credit. Don't worry. These aren't going to count for credit. That's why I'm rapid firing. Okay. So now into the dystopian future, which is not so dystopian, I guess. How do you believe the use of AI might impact your career plans or your prospects? Like, do you think that you will need to know a lot more about AI? Does that scare you? Do you think it's not going to impact your career plans at all? I'm just curious. All right. Going once. Going twice. Sold. All right. Last one for today. So when you consider the wide availability of powerful generative AI tools and their impact on education specifically, how do you feel? Are you, excited about what generative AI can help you do in your classes? Are you curious, but you're not actively using it? You don't really know or care? Are you concerned about potential issues? Are you anxious about those issues? So just let me know. Thank you in advance for helping me do my homework. All right, I'll give you another 10 seconds. Anybody walking in, don't worry, it's not for credit. Going once, going twice, sold. Let's see how we did. How do we feel? Okay, interesting. Mixture. Sorry, I didn't look at the answers for the other questions. I should have done so, but. All right, thank you all for helping me do my homework and informing me about what your thoughts are, because I also have mixed feelings. I haven't really explored it too much, and I haven't talked about it at all in this class. And if you use it, hopefully you're using it effectively. All right. Let's see. So back to chemistry. So this is where we left off talking about the standard heat of formation. So does anybody remember? Can anybody remind us how much of the product is made in a standard heat of formation equation? 1 mole, always 1 mole. And it's made up of the elements in their natural states. So these are 4 different heat of formation equations for different substances. And now we can actually use Hess's law that we also talked about last time to add up these equations and make them look like this bottom equation. So in this first equation, on the slide, we are making, because it's a heat of formation, we're making this sodium bicarbonate. Do we want that to be on the reactant side or the product side of our final equation? Reactant side. So what do we need to do? Flip it. And that means this is going to be positive. What else do we need to do to it? Multiply it by 2. Including that. Okay. What about the rest? Do the rest of them look okay? So number 2, number 3, and number 4 are the products what we want to be products? Yeah. So those are all okay. And they all have the right number of what we want. So I should really show you, you know, how everything cancels out, but yeah, I mean, let's do that. So if this carbon ends up on the product side and there's two of them, I'll rewrite that one for us. So if we rewrite that one, we flipped it, we're going to end up with this reacting to form 2Na plus H2 plus 2 carbon plus 3 O2. Right? So we multiplied everything by 2 and we flipped it. So now 2Na on the product side and 2Na on the reactant side, those cancel out. Here we have 1 carbon and 1 carbon, so that's 2 carbons on the reactant side and 2 carbons on the product side, so they cancel out. There's an H2 down here. Those cancel out. And then the slightly trickier one is that here, this is 1/2 and 3/2. That adds up to 4/2 or 2 oxygens. And here's the third. So all of our oxygens cancel out and all we get left over is the reactants we wanted and the products we wanted. So when we add all of these delta HFs together, we're going to get our total enthalpy for this reaction. So that is combining Hess's law and the delta H of formation, and we can plug that in our calculator. My calculator out. So multiply that first one by 2. 2 times 950.8. And then the rest are negative. So minus 1131 minus 393.5 and minus 285.8. So I got 91.3. So if we look up this reaction, it tends to get kind of difficult to look up delta H's of reactions because there's so many possibilities. But if we looked up that reaction, hopefully that's what we would see for the delta H for that reaction. All right, so that was a review of the delta H of formation and Hess's law. And just before I move on, just see, well, no, we'll see what you guys remember. I won't give it away. So here's a real clicker problem for you guys. The delta H of formation for oxygen gas at standard conditions, what should it be? Positive, negative, or 0? So let's predict our answer. You can talk to each other. We did cover this at the end last time. So review your notes if you need to, but talk to each other, and I'll give you 1 more minute to get your answers in. "20 seconds. Get those answers in. This one does count for credit. So if you still need clicker points, get your answers in. 5, 4, 3, 2, 1. Blast off. Going once, going twice. Sold. So letter C, good. All right, so it is 0 because oxygen gas, O2 gas, is an element in its natural state. So it already exists in that state. You don't need to make it. It's 0. So if we wrote that equation, it would look a little silly. it would be O2 gas reacting to form O2 gas, and delta H is 0. Alrighty, so I showed you that the when we add up some delta H formation equations, we can end up with an overall delta H. That's this formula that you're going to see on your equation sheet. Delta H of the reaction is equal to the sum of delta H, the formation of the products, minus the sum of delta H of formation of the reactants. So those, that N and that M, those are the coefficients for each product and each reactant. They're not usually all the same. So it really should be more like, on the equation sheet, you'll see it's, I think I wrote it as Ni delta H F product I. So it's just that the coefficient could be different. And these are the coefficients in the balanced chemical equation. So if we have a reaction going from our reactants to our products, we could make an alternate pathway and go to the elements in their standard states and back. So that would be doing, so if we go from the reactants to the elements, that's the reverse of the delta H formation equation. So that's why it gets this negative sign. It's the reverse. So negative delta H formation for the reactants and positive delta H formation for the products. Because if we're going from the elements in their standard states back to the products, that is actually a delta H formation equation. So that one is positive. It doesn't get a sign change. So that is the basis for this equation. So you just need to know how to use this equation, but that's the basis for this equation. And we're going to look at an example on the next slide. Okay, any questions about this formula so far? Okay. All right, so this is a pretty tough example, so we'll look at it together. So make sure you're following along, writing it down while we go. So benzene, C6H6, burns in air to produce carbon dioxide and water. So this is a combustion reaction. How many kilojoules of energy are released when 1 gram of benzene reacts with excess oxygen? So we need to know what the delta H for this reaction is first, before we can do the stoichiometry that we did in our homework for part 1. So the standard enthalpy of formation of benzene, delta HF for C6H6, is 49.04 kilojoules per mole. Delta H formation for water is negative 285.8 kilojoules per mole. And delta H formation for CO2 is negative 393.5 kilojoules per mole. What is delta H formation for oxygen again? 0. So that one we're not going to worry about. So now our equation, delta H of the reaction, is going to be, well, I'm not going to write out the sum part because we're actually going to plug stuff in. So it's going to be products minus reactants. So the coefficient in front of CO2 is what? 6. So it's going to be 6 times negative 393.5 plus So our sum, this is the left part of the equation. And our coefficient in front of water is 3. So that's the left part of our equation. And then we would subtract. Is there any coefficient in front of C6H6? No. So just 49.04. And then if we had this 15 halves of oxygen, it'd just be 15 halves times 0. So that part goes away. All right, so if we plug all that in, we will find that the delta H of the reaction is negative, hopefully I did this right in my notes, 367.4 kilojoules per mole. And if there's 1 gram of benzene reacting, what do we need to do with that 1 gram? Divide by its molar mass to convert it to moles. And once we have moles of benzene, or C6H6, then we're just going to multiply it by, come on, this negative 3267.4 kilojoules over 1 mole to cancel out our moles. All right, any questions about that? Products minus reactants. Okay, so you guys can try that on your own. We have a couple practice questions in here for you to try. But we're gonna go through one more thing here in chapter 9 before we start chapter 10. So last thing in chapter 9 is bond enthalpy or energy. So we talked about bond energy before. We talked about bond energy back in chapter 7, but I really should have called it bond enthalpy. It's really enthalpy. But we didn't know that word back then, so I called it bond energy. It is the energy or the heat required to break 1 mole of a particular bond. So heat and it's different for different types of bonds, right? So if we broke 1 mole of carbon oxygen double bonds, we would need to supply 799 kilojoules of heat. That's what we see in this table. You'll always have to find or be given a table. So in your homework, I don't know if you have any problems on this in your homework, but there is, in the references, there's tables of bond enthalpies. There's also tables of delta H of formation, which I do know you'll need to look those up. So use those references, general chemistry tables, to look up the delta H formation for your homework for chapter 9, part 3. And we have a new equation for this one. This one, the delta H of the reaction, is going to be equal to the reactant. I drew that a little big, but so the reactant bond enthalpies, which are positive, minus the product bond enthalpies, so the reason for this, does anybody remember what I said about breaking a bond? Is breaking a bond exothermic or endothermic? Endothermic. It requires heat. And is forming a bond exothermic or endothermic? So if breaking was endo, forming is exo. So it's exothermic. So that's why the reactant bonds, which are being broken, are positive, and the product bonds, which are being made, are negative. Negative is exothermic, positive is endothermic. So the way that I like to write this equation usually, though, is the sum of the bonds being broken minus the sum of the bonds being made or formed. Any questions about that formula? So this confuses students a lot because the other one we just looked at was products minus reactants. This one is reactants minus products, but just don't, when you're using them, you can't use this one if you're given delta H of formations. Like if you're given heats of enthalpy or heats of formation, you can't use this one, use the other one. It's got the delta H of F's in it, use that one. If you're given bond enthalpies, use this one because you don't have delta H of formation, so you can't use the other one. Use the equations and what you're given to know which one you need to use. Okay, so here's an example. We would use the bond enthalpy table to calculate the approximate heat. So I'm just going to refer to it on my slide. But the strategy here is we need to know which bonds are being broken and which bonds are being made. So we have to write out our reaction. If it's the combustion of methane, what's it reacting with? Oxygen. And what's it producing? Energy, yes. Okay, what else is it producing? H2O and CO2. Yep. Thank you. Good, good use of chapter 9 knowledge. All right, so is this balanced? No. We need a 2 here. And let's see. That makes this a 2 here. Now is it balanced? Yeah, I think so. Okay, so we need to see what bonds are being broken, so we need to go further. This is going to use your chapter 7 knowledge. We need to draw it. Lewis structures, yeah, woo! So how many carbon-hydrogen bonds are being broken? 4. We need to break all 4 of those. How many oxygen double bonds are being broken? Good. And then, so that's our left side. How many carbon and oxygen double bonds are being made? 2. All right. And how many oxygen-hydrogen bonds are being made? 4. Yeah. There's 2 molecules, but 4 bonds. All right. So then we would just look up those values in the table, plug them in, and solve. Any questions about that? So you'd look up whatever those bond enthalpies are, plug them in where I put the parentheses, and solve. Okay, so that's the setup. So now let's practice. So this one is for you guys. This one's an easier one. They're all single bonds. It's as easy as it looks. So we've got I2, Cl2, and 2ICl. Yeah, you know what that is. And they're all given up here. All right, so I'll give you another minute. It shouldn't take long. Talk to each other if you have to, but get your answers in. Megan and I will come around if you need any help. All right, just another 30 seconds or so. Get your answers in. I know you got other stuff to do, but let's work on this for now. All right, get those answers in. 15 seconds. 10, 5, 4, 3, 2, 1. Blast off. Going once, twice, sold. If you didn't make it, you didn't make it. Sorry. All right, good. 95%. So just 151 plus 242 for this one and this one, minus 2 times 208. All right. Any questions about that? All right, good. If you need it, here's my cheat sheet, but you cannot use this on quizzes or exams, remember? So only for practicing. All right, so the notes are posted, don't worry. But now we are moving on to chapter 10, which is very related. It might not seem like it at first, but it's very related. We're going to talk about delta H again. So chapter 10 is also about thermodynamics. So it's very, very similar, very short. So we'll spend the next 15 minutes or so on chapter 10. All right. So what do you think I mean by the word simultaneous? Or not simultaneous, spontaneous. Sorry. Yes. So spontaneous means it happens without any outside intervention. It just happens. So the forming of rust on a rusty nail, is that spontaneous or non-spontaneous? Yeah, rust forms spontaneously, but does it happen fast? No, not really. It could happen over weeks or months or however long, depending on how well you protect your things. So spontaneous reactions doesn't mean that it's fast. So keep that in mind. And I will have a demo on Monday of a spontaneous reaction. They can be fast or slow. And then non-spontaneous, that one needs outside intervention, right? You can't get the rust off of a nail without doing something to it, right? The rust doesn't just magically come off of the nail. That's non-spontaneous. Okay, so just another thing for you guys to know is that many, but Not all spontaneous reactions are exothermic. Some endothermic reactions are spontaneous. The demo that I did with the frozen beaker, that was spontaneous. I didn't have to do too much to make it happen. I just had to mix it together really well. But it was still endothermic. So that one was endothermic, but still spontaneous. Here's another version, ice that's melting. We talked about the phase changes. Melting, is that endothermic or exothermic? Endothermic, you need to supply heat to make ice cubes melt, but at a certain temperature, it's still spontaneous. So here is another thing for you. A process or reaction might be spontaneous at one temperature, but not at another. So this ice example, we're going to see on the next slide, that is one that's spontaneous at one temperature, but not at another. Any questions about this so far? Okay. So here's your ice versus water. If we are above the freezing point, melting point, if we're above 0 degrees Celsius, then it spontaneously will melt. Melting is spontaneous above 0 degrees Celsius. If we're below 0 degrees Celsius, melting isn't spontaneous anymore. Freezing is spontaneous. So this is actually non-spontaneous at temperatures less than 0. And this one is non-spontaneous at temperatures greater than 0. So chemists actually use this process a lot, even though it seems pretty simple. This freezing and melting process is used for something called recrystallization. So recrystallization is one way that we purify a reaction mixture. So basically, some chemicals dissolve at different temperatures. So we take a mixture and we cool it down very carefully, very slowly, to freeze out some parts of it. And then we filter it. So the stuff that didn't dissolve stays in the frozen part, and the stuff that did dissolve stays in the liquid part. And that's used to purify our reaction mixture. So if you went on to organic chemistry, recrystallization is an important technique that we use a lot, even though it's a very, very simple process. Question? Any questions? Okay. So usually, so I would say, I don't know if it's all, but I would say most spontaneous processes are irreversible. So what I mean by that is if a gas expands on its own due to a reaction, you need to add work to get it back to normal. You need to push that piston back in. So a reversible process cannot be restored to the original state by exactly reversing the process. a lot of chemical reactions that we talk about, especially like combustion reactions, they are irreversible processes. So, for example, combustion reactions, they produce a lot of heat. If you just reverse the reaction, you're not necessarily going to get everything back that you started with. You're not necessarily going to get all of the energy back or all of the reactants back that you started with. It's irreversible. All right. So, related to spontaneity and irreversibility is this idea of entropy. Have any of you heard of entropy before? Yeah, probably. So the entropy, it quantifies dispersion of energy. That's a very technical definition of it. And a change in entropy can be measured as delta S. So entropy is S. So we can say delta S is equal to the heat from the system over the temperature. That's one definition of entropy. The more common definition that you've probably heard of is that entropy is a measure of disorder or chaos, some people like to say. So if delta S of the system is greater than 0, so there's a positive change in entropy of the system, do you think that is an increase in disorder or a decrease in disorder? If you think it's an increase in disorder, raise your hand. For delta S greater than 0. Okay, good. So it's a weird concept. Increase in disorder, not so, or a decrease in order. So another way to think about the disorder is like the probabilities, the possibilities of the system. So if we have an increase in entropy, that means there's more ways that the energy is dispersed throughout the system. There's more configurations of the system. And our second law of thermodynamics states that the entropy of the universe is always increasing. So if you think about like the Big Bang, if you think about the beginning of the universe, it went from nothing to a bunch of stuff. So it increased in disorder. And as all that stuff kept expanding out into the universe, the entropy of the universe keeps increasing. It's always increasing. Now, I will say that's not always 100% true. But what it does mean is that the entropy of the universe, when it's greater than 0, that means that things occur naturally or spontaneously. The process occurs naturally or spontaneously. But there are processes that have delta S of the universe less than 0, or at least equal to 0. These processes require outside intervention. These are not spontaneous. So it is possible for a process to cause the entropy of the universe to not increase, but that requires outside intervention, and as soon as you're done intervening, it goes back to increasing. So delta S of the universe is equal to delta S of the system plus delta S of the surroundings. That's all there is the system and the surroundings. Any questions so far? I know it's a very abstract topic. Mm-hmm. Mm-hmm. Okay, so good question. So the question was about the ice example. So when we're at a low enough temperature, the ice freezes spontaneously, and that results in a change in delta S of the system. So the change in delta S of the system for the ice freezing is negative, but for the universe, it can still be positive because we also have what's happening in the surroundings. Yeah, so you got to consider both, which we'll do in the next couple of slides, but good question. Any other questions? Okay. So yes, this is the idea that you were getting at, is that the entropy of a solid is less than the entropy of a liquid is less than the entropy of a gas. So the idea is that for a solid, we've got very stationary molecules. Not much motion. I mean, they're not completely still, but there's not much motion. And over here, we've got a whole lot of motion. For the gas. So that motion results in disorder. So it's different ways that we can orient the particles, different ways that we can orient their energies. So the different ways that we can do that results in more disorder. So going from here to here, delta S of the system is greater than 0. Molecular disorder is increasing. Liquids are more disordered than a solid. That's what makes them free-flowing when you pour out a liquid, as opposed to a solid. So they sit right in the middle as far as their entropy. Any questions about that? Okay. We do have a couple more examples in the last minute. I know we're almost done and it's Friday. So this is another example, is an aqueous solution. So if we are dissolving, then do you think we are increasing or decreasing our disorder when we dissolve something in something else? Increasing. All right, so we'll pick up here on Monday talking about entropy and disorder. You should be able to at least start your chapter 10 homework. So I will see you on Monday. Have a good weekend, everybody. Be safe.